Well, hello everyone, and welcome to week 3 of the summer term. I'm Professor Rios. Hope you're doing well. As you probably or hopefully have or will read on the Blackboard lesson or page for this week 3 is by far the busiest. Think of it as a mountain, and this is the top of that. And so week 3 is it's the busiest. There's the most material, although the material itself, I don't think it's the most complicated. There's just a lot of it. Okay, so bear that in mind. By now, I hope you've watched the video on how to post a tweet link to Blackboard, and I hope you've watched the documentation and also the Google Earth sort of mini tour that I sort of put together. There are Google Earth questions throughout the semester, so please take advantage of that or simply ask questions. So let's begin with week 3, part 1. Let's put this in presentation mode and go from there. So this first lesson is, oh, and before I get going, as always, because these videos are a little bit longer than they would otherwise be during the regular term, watch it in pieces, half of it now, half of it later, whatever the case might be. But I do hope you watch them because they help to supplement the material in the textbook. Anyway, so climate and climate classification. So this right here is a beautiful image from the African savanna, a very specific type of climate, and we'll get into what that type of climate is. These are the objectives. We're going to talk about the Copeland system. It is a system based on climatic data, precipitation, and temperature. And it's pretty simple and straightforward, quite frankly. We have to define what climate is, and climate is a study of atmospheric conditions averaged over time. Think of weather as now, what's happening now, what's going to happen in the next few hours. Think of climate as the average of weather based on many, many years of data. The more data, the more years, the better. Okay? We talked about the idea of the global circulation last week. So this brings up the idea of different latitude zones from the middle of the Earth near the equator, where you tend to find low pressure and all seasons are wet, to where you tend to find deserts and all seasons are dry, or in the middle latitudes where we are, where all seasons are wet again, and the in between, where you tend to have either a summer or a winter that is dry or wet. So, those are places like, for example, Los Angeles, San Diego, uh, or more famously, the Mediterranean climate of, well, the Mediterranean. So, Italy, the south of France, Spain, and Portugal. Okay. So, looking at dry places, so the driest place on Earth is in the Atacama Desert of Chile. Remember, little pet peeve of mine, it's Chile, not Chile. You visit it, you don't eat it. Chile has the driest place on Earth. It basically has three reasons why it's dry. We're talking about downwind or downsloping winds from the Andes, near a cold ocean current, and near 30 degrees south latitude. So some parts of Chile have not received more than a millimeter of rain in a year, and some places have never recorded actual rainfall, at least since a station has been there. The wettest would be the state of Cherrapunji in India, lots and lots of precipitation. The hottest, officially, that would be Death Valley, over 130 degrees. The coldest, Antarctica, of course, where the temperature has dropped to minus 129. So these are climatic extremes, obviously. So there's a temperature that you can find in your textbook in these specific units, the idea of temperature for January or July, and you can see how it varies by latitude. And then the idea of temperature range, the difference between the high and the low for the year. So if you live in a place like Verkhoyansk in Russia, you can be exceptionally cold in winter, but exceptionally warm in summer. And in the US, you can see the difference between an Omaha, Nebraska, and a San Francisco, where San Francisco never gets really cold, but it doesn't really get warm. And the ocean has a lot to do with that. The idea of precipitation and precipitation across the earth, and where you tend to find lots of it and where you tend to find very little of it. These little climographs are very, very simple. They show you precipitation by month in blue bars. They show you the temperature for each month in that red line. And then you can see what the actual temperature range is for the year. So the more inland you are, the bigger that bump is, and the closer to the ocean you are, the smaller it is. The Copeland classification system is numerical. That is another way of saying empirical. It's based on actual data. And these are the benefits. Pretty straightforward. It's broken up into 5 letters and a six for Highland Climates. And this is how the book breaks it down, what the A climates are. What's the only one that is based on precipitation would be B. Those are the dry climates. Otherwise, you have polar, severe mid-latitude, severe mild mid-latitude, and tropical. Here in New York, we're somewhere between C and D. If you go all the way to Albany, they're definitely in D. If you go down to Jersey, it's C. So we're sort of in that middle, that boundary between the two climates. And this is how the first letter, what it means, what the second letter means, and what the third letter means. And this is a map. So this is from the Western Hemisphere. Again, notice where you tend to find in the United States, we have a CFA, most of the US. So that means mid-latitude mild climate, consistently moist, with the warmest month above 22 degrees. CFA. And that would be this right here. You can sort of decipher it for all the other climates. And this is what it looks like out west, or the east rather, hemisphere. Notice how there's variability depending on the type of climate and latitude and altitude. And notice how you can project that also to the oceans. Here is a climograph of a city in Africa. It's called Monrovia, and it would be where this dot is found. Notice little precipitation in the winter months, lots in summer, back to very little. So this is a place that is controlled by the energy of the sun, obviously, but also by pressure. As you go from low pressure when it rains a lot, high pressure when it doesn't. And if you turn to pages 186 and 187 of your textbook, you will see that you can find the map for the Copeland system. Again, the regional climate classification, you use the textbook, you turn to that page, you find it on the map, you read the color code, and it tells you that this place is a regional monsoon climate, AM. And it's shown because it rains a lot during one year or one part of the year and very little during the next. And there it is. There's where Monrovia is found. Again, these are the different climates, A, B, C, D, and E. And then there's this H climate, which is sort of a climate that's given to places where the altitude changes quite a bit. So you go from 1,000 feet to 8,000 feet, back down to 4,000 feet, back up to 12,000 feet in a very short distance. Again, going over the lettering. These are what the A climates look like. AF for tropical rainforest, all the way to AW, which is a tropical savanna. In fact, that image at the very beginning of the lesson is a tropical savanna climate. Tropical rainforest, lots of rainfall. Monsoon and tropical savanna, there is usually a dry season or a dry period that's involved. Notice for the tropical rainforest, there is no dry season. Here's what a tropical savanna looks like. Not too wet, not too dry. The B climates are referred to as deserts, BW, and steppes, BS. So a BW climate is truly a desert, whereas a steppe climate is a place that's like a grassland. It gets just enough rain to support that. Deserts, of course, tend to be found in areas of subtropical high pressure. Again, here's a climograph of a true desert. This is the city of Yuma, Arizona. And a steppe climate would be a place like Kazakhstan, where it gets just enough rainfall, as you can see here, but definitely more than this one, but not enough for it to be supporting trees and lots of vegetation. Again, this is where desertification is a threat, meaning areas that are already pretty fragile. Again, a review of the lettering, pretty straightforward to follow. These are the sea climates. Most of humanity is found in sea climates. Not all, but the majority. United States, China, parts of India, Europe. And here's a place like it's called Miyazaki, Japan. It is at latitude 32 degrees, so that would be like Atlanta, Georgia. Notice the majority of the rainfall is in summer. And sea climates that are more seasonal, this would be a city like Seattle or San Francisco. Notice the summer months are pretty dry, and most of the rainfall comes during the winter months. D climates are considered severe climates. That means summers are hot, but winters are really, really cold. So think about the middle of Alaska, the middle of Canada, Russia, Northern Europe. So again, look at the big difference between the low and the high in terms of temperature. Notice these big differences. This would be Beijing. This would be that city we talked about earlier called Verkhoyansk in Russia, way up north. Final climate would be polar climates, E, T, or EF. An ET climate is a tundra, so there's just a little bit of vegetation during summer. An EF climate is the Antarctic or Greenland. It's just covered in ice, even in summer. So again, that's what a tundra looks like. Notice not enough, the ground is frozen underneath, so it can't support trees. And of course, the permanently frozen, this would be Greenland or Antarctica. The highland climates are the ones that you classify, as I mentioned earlier, as a function of elevation changes. So this image here is Kilimanjaro in Africa. Even though it is in the middle of or near the equator, because it is such a high mountain, it can support snow very high up. So this is called a highland climate. And there you can see how you can go from desert to subtropical all the way to polar if you simply go up in elevation, which is what you're seeing in this image right here. All right, so the next lesson will be climate change. So let's go ahead and end that part. So I'm going to close this one. And we're going to move on to this one. Again, remember, if you need to sort of watch it in pieces, that's fine, whatever works for you. So, climate change is, of course, the most um, one of the most controversial or spoken about topics of the age. So, what I want you to do is these are basically, these big masses of ice that essentially regulate temperature across Earth. These are the objectives for the lesson. Again, to differentiate between natural and anthropogenic, which is human caused or aided, and all the different aspects of the lesson for today, or at least this part of the lesson. These are events that took place in 2019. I know it's a little bit dated, but the idea of anomalies or differences from the norm. And again, every year there are big, big, big differences in the norm. So, climate only tells you what you should expect. In reality, weather is what you get, if you want to think of it that way. So, this is the idea of sea level extent over the Arctic. Again, there's a normal minimum in summer, and there's a normal maximum at the end of winter. How much ice is covering the ocean? And that is related to climate change because notice this is where it should be at the minimum, but notice where we have been recently, with 2012 still holding the record for the least amount of ice cover over the Arctic Ocean. And again, here's a way of looking at it. If you're looking down on the North Pole, basically the minimum coverage is usually in September. And here it tells you what September in the 1980s looked like versus the 1990s versus the early 2000s versus 2010s. So it's getting progressively thinner and less expansive in coverage. And that has repercussions because ice tends to reflect energy back out to space. So if there's less energy being stored, if you're absorbing more energy, rather, you're melting more ice. So you are changing the very nature of the Arctic little by little. That's the fear, anyway. Here are some visual aspects of climate. The difference in Kilimanjaro's top in 1978 versus the early 2000s, or Muir Glacier in Alaska, or the collapse of Antarctic ice shelves, um, meaning you reveal darker looking ocean, which can absorb more heat, versus lighter colored ocean that's covered in ice. So that makes a bit of a difference. And there's history in the this is from the Antarctic. You can find these rocks with ferns and fern fossils. That tells you that the climate used to be different. When you look at the coast of Greenland, the west coast of Greenland, so that would be this right here, you can find these melt water pools that are found on the ice themselves. And when that water basically escapes into the ice, it basically bores holes and tunnels in it, making it weaker over time. Climate change can be short and it can be long. And these are some of the questions that are being asked when talking about climate change. So the idea of changes from the norm. This is the actual data record going back to the 1880s. That zero line, and it's not 0 degrees, but it's zero change from normal, so it's an anomaly, A positive anomaly means warmer than it should be, a cold anomaly, obviously, or a negative anomaly, colder than normal. Notice that from the year 1977 on, every single year has been warmer than the average, which is the zero line right here. So this is where we've been. And I can almost guarantee you that unless there's a big volcanic eruption on the planet, we're going to remain in this sort of warmer trend for a while. So, natural climate change can be short term and it can be long term. So, if you think about the idea of what's happened naturally before people really had any kind of significant influence, so before the Industrial Revolution of the late 1700s, everything that you see here, the ups and the downs, all happened naturally. People had no input or significance during this time. As soon as we became an industrialized society and planet and we began burning fossil fuels, notice where the black line goes. So the black line is all the data that we have dating back to as far as data was collected. So in the end, it's a pretty simple math equation. If more energy comes in than leaves, you're going to heat up. And that's where we are basically at this point. So there is more incoming solar radiation that's being kept as a function of greenhouse gases in the planet, like carbon dioxide and methane. So therefore, we are adding heat into the planet that isn't escaping. And this brings the idea of feedbacks, whether it be a positive feedback or a negative feedback. And while there is no single cause of climate change, these feedbacks have to be considered when you're talking about the idea of what's happening right now across Earth. Feedbacks are considered either positive or negative. So a positive feedback is reinforcing, a negative feedback is counteracting. Paleoclimate. Paleoclimate is a study of past climates using fossil records or other physical evidence as a proxy. Get it? An approximation. So you don't have data that goes back 5,000 years or 10,000 years or 10,000 years. So you have to use usually things like ice records or fossils or sediment at the bottom of lakes and oceans, or even human archives as far as you go back. So, this is how ice cores are collected. And they tend to be collected, of course, in Antarctica and Greenland, where there's a lot of it. And what they tell you is that the climate record that goes back thousands of years has shown this up and down nature. Humans have only really come around to be a significant part of the planet right about here near the zero line. So everything before that happened, frankly, naturally, without people intervention. And here's the example of the present day. And notice how there's been a warm period, a cool period, a warm period, cool periods. Do you see the pattern? And notice how the warm periods line up with high periods of methane and peaks in CO2. Okay. So the planet releases CO2 naturally in the form of volcanic activity and methane in the form of decomposition. The problem is humans are adding to that. And so we're making it worse. Let's see. This is what an ice core looks like. So it's like a straw of ice that you cut in half, and then you can literally count the rings, as it were. You can look at sediments at the bottom of oceans and lakes and help to figure out what temperature would those little creatures have existed in. Warm period or cold period? And by doing that, you get sort of a picture of what the climate would have been like 10,000 years ago, 20,000 years ago, 100,000 years ago. Because the deeper you go into the bottom of an ocean or a lake or even a river like the Hudson, the further back in time you go. The Human Archive record also can tell you something. This is a famous picture from England depicting a very, very, very cold, snowy, ice covered England. This is in 1565. England is not known for its particularly cold winters. So this image shows you that the climate back then was different than it is now. So that's sort of where the Human Archive can come in. All right, we talked about the idea of hurricanes and the impact that that has. The warmer the planet, theoretically, the potential for more storms, and the more storms that you have, the more damage, economic damage, that can be inflicted. CO2. There's this curve called the Keeling Curve, and this curve gives you an idea of climate or heat trapping chemical, CO2, a greenhouse gas. And this has been observed and recorded over Mauna Loa in Hawaii. And the up and down nature of it has to do with the seasons. So the peaks are basically in winter when there are fewer trees, so there's more CO2 in the air. And then the lulls have to do with, say, when there are more trees with their leaves out, meaning there is less CO2 in the air because the trees have actively converted it from CO2 into oxygen through the process of photosynthesis. Sea level rise, of course, is one of the most significant byproducts of climate change, one of the more obvious ones. And again, health effects, agriculture, lifestyle changes, economic impact. The big one is, of course, sea level rise. That's the one that is easier to see. Okay. This might be old, but this is still pretty applicable. The idea of climate change as a function of stability. Okay. So even though it's from 2004, so it's a full 17 years ago already, what's being mentioned here is still applicable this very, very day. So, anyway, worth reading. Some of the short term changes in climate have to do with either volcanoes or something like El Nino. So, volcanism tends to have a cooling effect on the planet because the dust and the chemical reactions shield sunlight from coming down into the planet. Of course, the idea of solar radiation, the idea of less energy coming in from the sun has a lot to do with it, makes a big, big difference. And this is measured as a function of sunspots. Again, just to give you a sense, that's what the Earth would look like compared to the sun. And one of these sunspots is basically as big as the Earth. Remember, 1 million Earths would fit inside our sun. That's how big it is. Or that's how small we are, however you want to think of it. Long-term climate change. So it's any systematic change in the statistics, the averages. They can be natural and they can be human caused. Pollution, urbanization, deforestation all play a big role in it. Here's the idea of loss of ice. So this is a glacier. then and the same glacier now and how it changes over time. Again, we looked at some of the temperatures earlier from global, southern hemisphere, northern hemisphere. In the end, we have actively been for the last 40 some years, 43 years, 44 actually, um, have been warmer than the average. And again, this doesn't mean 0 degrees as in temperature, it just means 0 degree different from the norm or half a degree difference from the norm on the positive or negative side. And again, how you look at temperature, you can look at a temperature record for thousands of years, hundreds of years, and tens of years. And all of humanity has basically all happened right about, you know, from about 11,000 years ago. That's when civilization really got going in terms of cities and culture and all that. The Industrial Revolution really began about 1750 or so. Milankovitch Cycle. So this is the idea of combining what happens and how does climate change when you change the orbital parameters of the Earth and the Sun. So you either have a orbit around the Sun that's either a circle or an ellipse. You have precession, which is how the Earth wobbles about its axis like a top. And of course, you have obliquity, which is the change in tilt. So right now we're at 23 and a half degrees, but we've been as high as 24 and a half and as low as 22. And that makes a difference in the seasons and who gets more sunlight, who has more dramatic seasons throughout the year. Ocean variation, and of course, extraterrestrial impacts. So I'm going to stop it there for this particular lesson. And we're going to be moving on to the biogeographical aspects of the lesson for the week. All right, let's get back to the lesson, biogeography and soils. So lesson objectives. The linkage between soil and climate. And what biogeography and what the biosphere happen to be, the difference between the two. We're going to concentrate mostly on the plants, not the animals. There's, of course, a human impact and a human imprint. Hopefully, that's become really, really, really obvious before you even took this class. Some of the important terms and concepts. So, we've addressed the atmosphere and the hydrosphere, ocean and air. We're talking about this now. Eventually, we'll talk about that. So, this is water, air, living things, the hard rock and crust of the planet. So the fact is, the biosphere is highly variable. It really depends where you are. Some areas are very, very productive, like tropical rainforests. Some areas are very, very weak and highly unproductive, like deserts and the polar regions. So, as a function of that, you have to think about the idea of vegetation and climate and how it changes as you go from, say, in the United States, New York, to Illinois, to Wyoming all the way to California. You go through different biomes as you travel across this country of ours. And you can do the same thing in Africa, in Europe, South America, Australia, Asia. Doesn't matter where you do it, you're going to find big differences in vegetation because of climate. Okay, so you have a place like Charleston, South Carolina, and Yuma, Arizona. Same latitude, basically. And they have very different climates, and therefore they have a very different vegetation profile, just as a function of where they're located and their proximity or distance away from water. And there are other things like temperature, slope, the idea of what makes up the rock near them, how much sunlight they get, photo period. So, conservation, the careful management of natural resources. And this stems from lessons learned after the Dust Bowl era of the 1930s in the central part of the United States. Here's the idea of conservation and biosphere. There is the border between Haiti and the Dominican Republic. There is literally no difference between those two places in terms of climate and rainfall. The only difference is how they are managed. Clearly, the Dominican Republic doesn't place as much emphasis on the usage of that biomass. Haiti does. But you can tell that because there's been so much deforestation, when the rain falls, which is heavy in this part of the world, the tropics, the Caribbean, there can be a lot of loss of soil as a result. And here's the idea of soil loss. This is from the island of Madagascar, which to be a tropical rainforest. It should look like this dark green you see here, but everywhere. And as a result, because there are so many fewer trees, all the soil gets scoured out by heavy rainfall and it winds up on the ocean. So the beaches look like chocolate milk when they should be this color. Here's the idea of um, erosion risk from low to high to very high. The carbon cycle. And there you see it. Volcanoes, deforestation, photosynthesis, people, uh, industrial processes. The up arrows implies the removal, and the down arrows imply the reintegration into the landscape. Soil, what is it? Well, it's made up of water, mineral content, organic material, and air. Water depends on the climate that you happen to be in. So essentially, adding water to soil, depending on the type of soil, you can get some of those nutrients making their way down the different layers. Soil becomes progressively more mineral as you go down, as you get closer and closer to bedrock. And these are the factors in forming soil, and there are 5 of them: climate, organisms, topography, parent material, and the most important, lots and lots of time. Soils don't just form in a few days, in a few weeks, in a few months. They take years to form. And you have to have the right type of climate, Plants and animals that die and decompose. Topography, is it flat? Is it hilly? And then what's the rock material? So here's, for example, a desert location. Notice how white sandy the soils are here. Or look at a place like the Peruvian hills approaching the Andes. You can see it rains a lot here, and there's a lot of organic material. It's hot all the time. It rains a lot. Or this, which happens to be from the Canadian pine forests. So it rains enough. There's plenty of snow. It's a lot colder, and most of the time the water is frozen, so there's no decomposition taking place. So this happens to be a very different kind of soil than what you would find here in the tropics. Animals make a difference. They burrow holes in the ground. Water and air can get in. Topography makes a big difference. Is it hilly? Is it flat? So in New York, if you go to Harriman State Park, for example, and you climb up and down, you love to go hiking, the soil and the bedrock are almost at the same level. It's exposed. Now, if you go to a place like Iowa or Illinois, you have to dig really deep down in order to get to the rock. In New York, it happens to be exposed quite a bit. Again, this is, if you think of a layer, this is the soil, this is the bedrock, and then this thing called regolith is sort of a combination of the two. These are the soil forming processes. You can add, you can transform, you can deplete, and you can move it around. So these are the soil forming processes. Again, the different ways in which these particular ones come into play, from addition to transformation to depletion, which is loss, to translocation, which is the movement of material away. And this is right from your textbook. The different layers. And some of the different terms for eluviation, iluviation, and leaching, and what each of them means. Some of the basic soil properties, the most obvious would be color, texture, and structure. So the smallest would be clay, the next biggest would be silt, and the biggest would be sand or gravel. Color, well, that's pretty obvious, right? Depending on, if it's a salty soil, it'll look lighter in color. Texture brings up the idea of porosity and permeability. A soil that is porous and permeable lets water through rather easily. A soil that is porous but not permeable means the water is going to get stuck and it's going to be like mucky and stagnant. Think about sand. When water hits sand, it gets wet, but it transmits that rather quickly. Sandy soils don't tend to flood as easily. So there's a definition of the two. Again, the difference between porosity and permeability. And here's the idea of something like clay. Clay is a very porous but not permeable soil, meaning it soaks up the water, but it doesn't let it pass. Sand is the most permeable, or in this case, gravel because it's bigger. It basically allows the water to go through so it doesn't really react with it. It just basically goes right through it and it dries up a lot more quickly. This is the soil triangle. You find this in your textbook. And that brings us to the next part, which will be part 4, biogeography and ecosystems. Oh, there you go. So this part here, this is an image. I love this picture. This is from the African Savannah, thunderstorm in the distance. Notice it is a AW climate. There are a few trees, but it's mostly grass. So this area gets rainfall, but there's a significant part of the year where the climate here is very dry. So the lesson objectives, the key terms and concepts. Again, same two definitions we talked about last. We talked about this before. And now we're definitely ending this section. Talked about that. So some of the processes. So the first one is photosynthesis. It's essentially the idea of turning water, carbon dioxide activated by sunlight, and you create a carbohydrate, which is a simple sugar, and oxygen. So this is the most significant biological process that happens on Earth. This is how plants grow. Animals eat plants. We eat the animals or the plants. And that process continues. So solar energy is stored and converted into a simple sugar, a carb. And then tropical regions are responsible for about 20% of the planet's oxygen. They generate a lot of it. Notice the greener the map here, the more photosynthesis is taking place. Notice you do find this where things are wet and where things are sunny and warm. So deserts don't showcase that as well. The idea of respiration, think of it as the opposite of photosynthesis. So in respiration, you consume a carbohydrate as you breathe, and you basically generate CO2, water, and heat energy. Think about you exercising. You're running, you're breathing harder, you're consuming more oxygen, and you are burning the energy stored within your muscle fibers. The net result is you sweat, H2O, and you feel warm, heat energy. Okay? So that is the idea of respiration, the opposite of photosynthesis. And plants can often do this. Plants will respire when they are under stress. Net primary productivity. It's a very key point. It's measured in kilograms of carbon per square meter per year. And you tend to find the highest values of net primary productivity in areas that are closer to the equator, in areas that are warm, and in areas that are wet. Notice how there is less net primary productivity the further north or the further south you go. So linking it all, photosynthesis and net primary productivity, each of these is limited by physical factors, and factors are limitations. For example, is it too dry? Is it too wet? Is there something like a forest fire or a hurricane or a volcanic eruption that limits any of these. Physical factors can be in short supply sometimes. So if you think of deserts, they can be warm, they can be sunny, but they're missing water. And therefore the net primary productivity is low. Okay. So you can have a range of optimum conditions. You have an upper threshold, that's good. Think about an embarrassment of riches. No, there's nothing missing. Or you can be on the low end. So the low end would be a desert and the high end would be a forest. Meaning there's nothing in short supply here. There's lots of things in short supply, or one significant thing in short supply. For example, water. Ideally, you want to be somewhere in the optimum condition range. And here's the idea. And in some cases, like trees or animals, they have to basically be in tune with a very, very specific set of conditions. So if it gets too hot, too warm, too cold, too dry, too wet, that specific organism, whether it be a plant or an animal, will not live or exist in a particular area. Others can be more adaptive. And as a result, as it says here, species with wide ranges of tolerance to most of these factors will be widespread. Again, the role of climate is significant. In tropical areas, there happens to be a tropical rainforest or an AF climate, you tend to find there are no missing factors. So therefore, vegetation grows all the time, very, 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 very quickly. In some places, you'll have a dry season, and during that dry season, things go into safe mode, as it were. Okay. So think about again the idea of physical factors: temperature, physical factors, water, places that are wet all the time, places that have a dry season, places that have dry seasons every season. And the idea of light or photoperiod. So the further north you are, the biggest the difference between summer and winter. So summer can have long, long days, but winter can have long, long nights. If you live near the equator, your photoperiod is roughly the same all the time. So it's much more reliable. So actually, we will forgo this one and get into the biomes. These biomes are ecosystems as they were, and they're influenced by all these factors right here. We're going to focus on terrestrial. And of the terrestrial, we have these different biomes from forest, savanna, grassland, desert, and tundra. So a forest that's a tropical rainforest may be small, but is very productive. So tropical rainforests tend to be the most highly productive of any terrestrial ecosystem, followed by temperate forests, that would be New York, or the taiga, which is northern Canada, Russia. So the least productive. These are the different biomes across the earth. And as you go near the equator, as you head in this direction, it gets progressively drier. As you get in this direction, it gets progressively colder. So in New York, we are roughly right about here. We're colder than tropical regions. We are warmer than northern coniferous regions. We're not as dry as a grassland. We're not a desert. So we fall somewhere in this area right here. Not too dry, not too cold. Here's the idea of tropical or A climates where you tend to find them. C and D climates where you tend to find them. D climates or boreal forests where you tend to find them. Here's what a savanna looks like again. Again, enough rainfall for trees to grow, but not enough for it to be a jungle. Where you tend to find tropical savanna. Notice it's related to an A climate. A grassland. You could find this in the US in a state of eastern Colorado, Kansas, Nebraska, Wyoming, western Oklahoma, western Texas. Deserts, of course, B climates, and then tundra. So this is a great picture here because it shows you a few trees, but not a whole forest of them. And here you see the fact that it's basically like mostly the transition between a pine forest and the tundra. Here's what the tundra itself looks like. No trees anywhere to be found. This is the idea of limitations. So for example, there are places that have no limitations, the tropics, places with seasonal limitations, that would be New York, and places with permanent ones. So the mid latitudes, so here's the tropics, lots of net primary productivity, lots of rainfall, sunlight, and heat. As you go into mid latitudes or tropical wet dry climates, less productivity. And as you go into deserts, very, very limited. Okay? So that is the lesson that I have for you. I know it's a lot of material. I get it. It's a lot of material to cover one in 1 week, and that's just the nature of the summer term. So take it in chunks, go over it in pieces, view one part of it, then the next. Do it all at once if that works for you, whatever the case might be. But I do hope that you take advantage of the videos. And if you have any questions, let me know as soon as you can. Otherwise, I hope to talk to you soon. And if you have any questions, send them my way. Bye.